So you can think of the memory map now as this context. It's a context for interpreting virtual addresses. So what I have, if I give you the page map, I tell you everything you need to know to turn a virtual address into a physical address. And in fact, if I wanted to run more than one program at once on my machine, I might be able to have them sort of living together simultaneously. Okay. Notice that in this particular instance, I have, if you will, two virtual memories that I'm dealing with. One for the browser and one for my email program. And they both have addresses that say, they both start at 0. They were written as if they had the entire machine to themselves, but I'm going to have a different context for each of the two programs when they run. And so when the browser says, give me location 0, it ends up at this physical page. And when the email program says, give me location 0, it ends up at a different physical page. Right? And if I had a rapid way of switching contexts, as I went from one program to another, each of these programs could all feel that they have, in a sense, the machine to themselves in terms of address space. And by simply quickly changing context, and what do I have to do to change the context? I'd have to go change all the entries in the page map, which isn't trivial, right? There's a lot of entries in these page maps, but we'll solve that problem in the next slide. If I could change the context quickly, I could go from running one program to another, instantaneously almost.
Question?
Yes?
So some programs would use the same things in memory, though, right? So
You mean shared code?
yeah.
Okay, so that's a very good question. What do you do with shared code? Well, what are our two choices? Our two choices are to make sure that the shared code ends up in the same virtual address space in everybody. And then we simply arrange the context to take, if this is the C library, and this is the C library here, we make sure they all map to the same physical memory. Actually, many libraries are written to be what's called position independent. They can actually run in any location in virtual address space. And so that actually simplifies things a little bit. Okay, so the sneak preview really is that we're starting down the path of saying, gosh, we really like this beta that we built, this virtual machine. Seems like this machine, this hardware. But it turned out to actually make running programs in the modern environment where you're trying to do 18 things at once, wow, email, 6004. I know that doesn't take very much, but occasionally you do 6004. What we'd like to do is to say, look, everybody gets their own copy of the beta, a virtual beta. A virtual meaning that what we're going to do is we're going to take the physical beta and multiplex it among all these different tasks. And each task feels that it has an entire beta of its own. It has its own virtual address space and everything, its own stack. And I don't have to say, well, what mix of programs do you want to run, and I'll compile them just so. I can say everybody gets compiled exactly the same way. Everybody starts at 0, so forth and so on. So this is going to be the topic of some lectures coming up. Rapid context switching? Well, in fact, if we sort of, for each context, think of that as an extension of the virtual page number, and we use, we sort of concatenate a particular virtual page number from a particular running program with, in a sense, an index for the program, a context number, we can use that, run that through the translation process. So we can think of this as really a huge virtual address space that not only includes the virtual address space for a single program, but additional copies of the address space for everybody who's running. Okay, so we might have, another 8 bits of context, and we'll just treat that as more virtual page number. So then we wouldn't even have to fix the page table. The page table, of course, would be correspondingly larger, but the translation process would run sort of unchanged. And so we can do rapid context switching simply by changing the magic number in this register and going from there. Okay, so here at the end, just to finish up, so far we have a cache and we have a memory management unit. What order should they go in? Should the cache be listening to the virtual addresses of the CPU? Okay, in other words, this process seems a little slow, so this is sort of attractive. The idea, look, if you ask for a virtual address, what I'll do, this is what's called having the cache virtual addresses, right? So the cache, what it has in it is virtual addresses. What the tags are virtual address tags. The numbers are inside the tag field are pieces of the virtual address. So we'll respond quickly whenever we can. What's the problem with this arrangement? Well, when I change context, now I have to flush the cache. Because because when I change context here to run a different program, now a particular virtual address corresponds to a different physical location, a different actual value for a particular address. And so that means whatever was in the cache has to change. If I switch the order of the MMU and the cache, I solve that problem, because now the cache is caching physical addresses. So I've already done the translation to physical address space. The trouble is I have to wait until the MMU process is complete before I know what address to look up in my cache. So that seems to make things longer. But the cache uses the low order bits of the address as indexed to figure out what tag field to fetch when we're using an n-way set associative cache. The MMU uses the higher order bits of the virtual address. If I said physical before, I meant virtual here. This is the virtual address coming from the CPU. So the low order bits index into the cache, the higher order bits index into the page table. The MMU, while I'm looking up in the cache, the MMU is also looking up the physical address translation. I end up with a tag field coming out here and a virtual page number coming out of the MMU at the same time, basically one SRAM delay. And so if I can choose the parameters of my machine and the design of my cache and the design of my memory map in such a way that that the virtual page number and the information, the index to the cache do not overlap, I can actually run these two in parallel. And a lot of modern machines sort of do that.